CPAP Bryson Scholar Poster Competition, which occurred earlier in February. And so Paul had graciously allowed us to use this setting here with the CPAP seminar, which is also sponsored by the same set of funding, the CPAP Bryson Fund, organized through the Center for Climatic Research at the Nelson Institute. Mike Notaro is the director of that. But in my role as organizer of the poster competition, I get to do the fun thing, which is we have a few of the students here, not all of them, but we're going to recognize all of them. But this was our 14th annual Bryson Scholarship Poster Session. This was on February 9th. We had 52 students competing from 21 different departments and centers. Everything from atmospheric science to ag econ to plant pathology and math. And these really reflect kind of the role of Reed Bryson's kind of broad polymath perspective on what counts as climate, people, environment science. I think that's also reflected in the work that's going on today by our very own undergraduate and graduate students. And so we're very, very grateful that we're able to give out awards through this very generous funding, which is always welcome for more donations, by the way. We're able to give out awards between $375 and $1,000 per poster, which is pretty substantial award for a poster competition, and I think it's a really useful thing. We'll continue to do this. I'd be happy to have a new organizer next year, but we'll keep doing this as we can. So we're going to go ahead and just give out awards, and if you are here, please come up and receive your certificate and shake hands and look and smile and move on. So for the undergraduate poster competition, we had 3 winners, 2 runners-up and 1 winner. So we're going to go to the runners-up first. First up is an undergraduate researcher in atmospheric oceanic sciences, so come on up, Knight Zawalski. On her poster that she presented on terrain impacts to microphysical processes of deep convective storms in central Argentina. And so, certainly some questions on hydrology that will come up. Okay, and our second runner-up was a student in chemistry, Eliana Bernat. I don't know if she's here, but her poster was on covalent adaptable networks, building the next generation of recyclable plastics. So let's give her a hand and all this. All right, and then with our graduate student awardees, we had 2 co-winners, which we'll announce in a minute, but we'll start with the runners-up. And so we had 3 runner-ups based on the judging. The scores were really close, and I really appreciate, by the way, we had about 24 judges or so who took the effort to review all these posters, and we're very happy to have them, and they gave really great comments and feedbacks. Oh wait, I forgot to announce the winner of our undergraduate. This is why I didn't sort these properly. But yes, forgot to mention the winner of the undergraduate competition. Let's step back. Is an undergraduate researcher in material science and engineering. That's Leo Liu, who's come on up. Here we go. And your poster title is about covalent adaptable networks building the next generation of recyclable plastics. So that was your poster. Sorry, the last one was safer solar materials, designing 2D perovskites and mixed solvents. So it's that kind of day. But you're doing great work, and congratulations. Now let's move on to the graduate students. We have 3 runners-up. The first one is a graduate student in atmospheric and oceanic sciences, C.D. Liu. C.D.'s poster was Down to Ice, Satellite Detection and Analysis of Iceberg-Sized Distributions. So, also hydrology. Right, congratulations. We also had a runner-up in soil and environmental sciences. We had 2 soil and environmental science runners-up. One of those I know is Su Chao Yi, who I believe is not here. Su Chao's graduate student in soil and environmental science, whose topic was crop diversity enhances the resilience of crop yield to excessive rainfall. And so this is going to hand to Su Chao Yi. And then our other runner-up was Sony G. who's also a graduate student in soil and environmental sciences. Are you here? Using mid-infrared spectroscopy to estimate soil microbial properties at continental scale, which is pretty cool sounding. Alright, so let's give another hand to this. And we had a tie for winner this year. And they are both graduate students in atmospheric and oceanic sciences. So first up, because I see her right in front of me, is Kara Scalpone, who is our co-winner. Her title is Understanding Wintertime Air Pollution, the Role of Building Heating Emissions and Temperatures. So congratulations, Kara. And then our co-winner, our other winner here was also from AOS, I believe she's not here, is Shane Visaga, who is a graduate student in AOS, and her topic was also air quality, but this time on biomass burning transport during the 2019 Camp 2X, using Musica and regional refinement over Southeast Asia. And that is our winning posters. We had a whole bunch of topics, everything from machine learning and AI, Earth system models, soil erosion, fish habitat, heat islands, indigenous agricultural practices, agrivoltaics, wildfire impacts, microbiology, nitrogen cycling, climate change impacts to wine yeast even. And so we hope to be able to see more of those folks next year as we have more posters to compete with. But I'm going to move on and turn it back over to Paul Block for your regularly scheduled programming from our distinguished speakers today.
Great. Thank you very much, Hunter. I really appreciate it.
Two announcements. If you presented a poster and you still didn't grab it, it is sitting in 248 in this building, and so it's still available. If you want it, they will get recycled soon otherwise. So please come grab those. Maria.
That was one. You had two announcements.
Yeah, that.
Okay. Very good. All right. I am just going to turn it straight over to Dan today to announcement.
All right. Well, I have a very long and impressive bio here for
very short. I already spent 10 minutes.
Yeah. So I'm very happy to present Venkat. Lakshmi is a professor at University of Virginia. Came there by way of University of Roorkee, and then master's at Iowa, PhD at Princeton. And so I guess we're like academic cousins 3 times removed or something from the Princeton and Iowa connections. But anyway, I guess I'll highlight maybe just 2 things. One is that he is currently the president of the hydrology section of the American Geophysical Union, which I believe is the largest section in AGU, if I'm not mistaken.
Second largest.
Second largest, okay. And then I just want to, say thank you, basically. So Venkat, amongst many other talents, is always very supportive of early career folks. And so I had a chance to visit UVA a couple years ago and see his research group, and was impressed at how tight-knit a little community that was. Not that little, actually. And then also, he's done a lot to support me and others, through assistant professor years and onward. So thank you. And I'll turn it over to you.
Thank you, Dan. Thank you so very much. And I asked Dan just before we came here, when Michigan played Wisconsin, whom did he root for? He gave the right answer. He said Wisconsin because they pay my paychecks. Thank you so much. Thank you so much for coming. I've heard so much about Wisconsin, and this is my first trip. And one of the things I was struck by was you're closer to Chicago than University of Illinois, which I did not know. And second of all, this department, I have known people here for a long time. So there was a professor here called Eric Smith. I think he was a very big pioneer in remote sensing. And then, of course, I knew Grant Petty very well and used to see him a lot at conferences. So, it's an honor to be here and be in a seminar, as well as my former boss from UVA, Craig Benson, who was here and was a big badger here. So my title of my talk is Progress and Challenges in Hydrology, and I'll jump right into it. So the problem is, land surface is very heterogeneous for those of you who do hydrology. And, the heterogeneity comes from different variables. And, if you just focus on the material part of it, it's soils, vegetation, and topography. I mean, there are other inputs which we will also come to. Hydrological variables are sparsely, if observed, in situ. So when you look at, inputs, precipitation, ET, soil moisture, or outputs, stream flow, groundwater, they lack a long record. So if you ever find a station, a rain gauge with 100 years of data, that's pretty rare. And having that publicly accessible to people is very rare. And then Earth observations, on the other hand, or remote sensing, satellite remote sensing, cover large spatial areas, but they do averaging. That's the sad part. And also they're very sparse, so you have overpasses once every few days. So they lack a long data record. We're talking about 30, 40 years. The longest one, and I'll show you, is Landsat, 45 years. But models, which many of the people in this room do, is a representation of physics that may be approximate. So what are the challenges? And this talk will be on 4 challenges and some progress. Some of these challenges, most of these challenges, or all the challenges, I'm going to present results from my research group with an obvious bias towards our results. But there are a lot more than the ones I present. And secondly, not all of the challenges I devote equal amount of time, because I thought some of them are more important than others and more time to them. So there are 4 of the challenges which I come up with. Do Earth observations compare well with in situ counterparts? Because we have Earth observations, but somebody may ask, is that really correct? Now, how important is precipitation in hydrological modeling? This is a very, very important question, and something which will, everybody asks for a long time. And how can we get higher spatial resolution and deeper into the soil from Earth observations? So the thing is that Earth observations are on scales of kilometers. And when people do catchment modeling, they want it to be smaller, in the order of hundreds of meters, or even smaller, maybe a couple of meters. So how do you do that? And the last one is a nod to AI ML. How do we go from gauged and gauged watersheds to poorly gauged or un-gaged watersheds, which is very, very quite important in our line of study. So, when we talk about Earth observations, one of the very interesting studies was the NRC-NASA Decadal Survey 2017-2018, which was performed, and it exists online, so you can read all 520 pages of it, with 100 pages or so devoted to hydrology and water resources. So the part of hydrology, which was the grand challenge, was this part, which is water and energy coupling, prediction of changes, availability of water coupling with biogeochemical cycles, and hazards, extremes, and sea level. So if you look at all of these, there is different science questions which are addressed in that decadal survey, and how Earth observations can help you to answer those science questions. You still need in situ observations, you still need models, but how can Earth observations help you? And how do you plan the next 10 years, in 2016, 2017, 2018, next 10 years of it? And we are almost at the end of that 10-year period, and the Academies is getting ready for another decadal survey. So these are the kind of questions you want, and this is actually derived from that report. So when you talk about Earth observations, we have been doing Earth observations since the 1980s. And one of them, Landsat, for example, is available very easy these days on Google Earth Engine. And most of the people in the community of hydrology use Google Earth Engine, because you do not have to download the images or the satellite data. You can just use it directly, produce the results, and it will be all done on the cloud. So you don't have to spend much time to input-output processing, or spend hard drives on your computer. So we start with Landsat, vegetation, land use, land cover from the 1980s, and then AVHRR, Advanced Very High Resolution Radiometer, did vegetation index and surface temperature for a long time, and it's still going on. It's in a NOAA series of satellites. And then we come to wetness and rainfall, and I will pause for the rainfall, which is more recent, from 1999. It's called the GPM iMerge, which is an integrated blending of all the data sets from 1999 to current, and this is available from 1999 or 2000 to 2026 right now at 1 kilometer, 10 kilometers, 30 minutes temporal repeat. And I know Dan has worked a lot with students on that. The other part is soil moisture, and there have been a lot of studies of sensors in orbit in order to retrieve soil moisture, and some of them have been not as optimal to observe soil moisture, because you have to have the optimal sensors to look at these things. And one of them, which I did with my doctoral dissertation, was SSMI, and so it's not very optimal at 19 gigahertz, but now we have 1.5 gigahertz on the L-band, which is much easier to do. And then 2 other ones are total water and water level, GRACE, which is Gravity Recovery and Climate Experiment, which we use a lot to see the total variability of the water in the whole column, right from groundwater all the way to the top of the atmosphere. And SWOT, which is much more recent, results are just coming out right now. It is the surface water and ocean topography, and it can tell you the elevation change in water level. So actually it can compute discharge and it can compute water level, which is very useful. And we have been just completing a paper comparing SWOT observations to in situ observations at a couple of hundred sites in South America. And then we have atmosphere, standing here in the atmospheric sciences department. I should say that AIRS AMSO has provided profiles of atmospheric surface air temperature and water vapor for a long time now. So if you put that all into a cartoon, this is how it looks. And if you look at our simple equations of energy balance and water balance, many of these variables are sensed by different sensors, different time periods, different spatial resolution, different time of day. So it's all a hodgepodge because nobody else ever thought of putting it all together at the same time and doing it and back. So nobody can actually close the water or energy balance just by using observations. We have to rely on models for much of it. So, but this is how it looks, and this figure also appears in the Academy's report. So you can. So then if you look at this from the long time, from 2011 to 2026, a period of 15 years, and if you look at the monthly precipitation from GPM iMerge, and then you look at the surface soil moisture, as the precipitation goes up and down the ITCC in Africa, you can see the soil getting better and drier, for example. You can see the vegetation growing and decreasing, as you see, going up and down. And then the terrestrial water storage, the total water in the system, the vertical column I was talking to you from GRACE, you can show it's increasing or decreasing depending on the rainfall. So this kind of movie is great, but it embeds itself in itself many spatial scales and many temporal scales, which is worthy of dozens of analysis. So if we start talking about hydrology, and in today's climate, sorry, pun not intended, I would rather not talk about climate, but I would talk about hydrological extremes. Because when we talk about climate change, basically we're talking about occurrence, or more frequent occurrences of extremes. And so when I say hydrological extremes, I mean floods, I mean droughts, I mean landslides, permafrost thaw, and wildfires. All of these are related to hydrology. And all of these impact society. And so much so that if you look at the 2025 NCEI map, and this is just directly from that website, you can see there have been about 20 or so of these billion-dollar disasters, hydrological extreme disasters. And this does not count loss of human life. This is not counting loss of human life. I mean, we're not talking about people who died in these actions. So there's a lot of these. There's a lot of losses. So when you talk about hydrological extremes or hydrology, even for just United States, there's a lot of ROI on the investments we can expect because of understanding these and providing advanced warning. Understanding the historical events is the first step in prediction, successful prediction. And this is a cartoon of where the hydrological extremes cost, and this is a couple of them just thrown together from NCEI and USGS, and all of these are in the billions, and we're talking about huge impact on human society. And again, this does not account for loss of human life. That we can't put a price on. So when we in hydrology look at climate change, we are not looking at CO2 because that's not what we do. So we look, the most important aspect of hydrology is precipitation. If there was no precipitation, there would be no hydrology. So I always joke with the people next door in my office whenever it's raining. I say, that's not a 4-letter word, that's job security. Because if there's no rainfall, there's no job for me. So rain or precipitation is the most important, and we've written a paper. The slide I have not put in this presentation is the first principal component, or the most important principal component in the hydrological cycle is precipitation. So if you look at precipitation, one of the things with IPCC is more intense extremes will contribute to a shift in precipitation distribution. And this is a paper by Sonia Selivaratne. So we did a simple experiment, which was eventually published in GRL, where we took the observations. These are in situ observations in Europe. You know, they have a long record of EOPS, which is gridded of precipitation, daily precipitation, and you arrange for every grid, you arrange the precipitation in a decreasing order, the most precipitation first, the second most, the third most, and then when you hit 50% of the annual precipitation, you stop, and that's the number of days required to fill a 50% of your bucket, WD50. And so if you take 2 periods in that, 1986 to 2021, the more recent period, and 1950 to 1985, you will see that in the more recent times, the bucket is filling with lesser number of days of precipitation, which means the number of bigger storms per day is increasing. So actually precipitation itself is not changing much. You know, it's pretty flat, I mean, over time. But the number of bigger storms per day is increasing. It's almost like instead of giving you 21 meals a week, breakfast, lunch, dinner times 3, if we give you 10 meals or 5 meals, I mean, obviously it's not going to be good for the human health to do that. So that's what's happening. So more storms, same precipitation, but more bigger storms, and actually more number of dry days. And they're doing that right now, actually. So that's a problem, and that's climate change. You can call it hydrological extremes in the current climate, but it's what it is. And then we did the same thing. This is with GPM iMerge, and also in GRL. So we do this, but again, we don't have it from 1950. We only have it from 2001. And we also, again, split it up into 2 parts, and you can see that the negative dominates, meaning that even in the current 2 decades, there are more storms with more precipitation filling up the bucket for 50% than, you know, having that. So it's best for hydrology if it is a nice, slow sprinkle. That's why most people say that you should snack throughout the day and not have too much big meals and all that stuff. So same thing. You know, the land surface should snack all year rather than having too many big meals in some sense. So that's the thing, that's where it is. So that's the background of how hydrology links to climate. So the first challenge was, do Earth observations compare well with in situ counterparts? Since we have been talking about precipitation, we have lots of publications on precipitation, and actually GPM iMerge has, you know, many publications trying to show how good it is, you know, compared to in situ observations. So this is an example with one of my PhD students. This is the lower Mekong River Basin. We have not done the extension to China, and all of these dots are locations of rain gauges. Of course, the dots are very big because that's a big area, but they're small, it should be small. So these are all the locations of the rain gauges, and if you look at the precipitation over here, the dry season, the wet season, from both the TRIM, which is the NASA product, the CHIRPS, which is a product from UC Santa Barbara, and the in situ, which is these rain gauges, you can see they show reasonable, you know, comparisons. And again, you're comparing apples and oranges, because one of the things, if you go back to this, which is very important, in the more elevated regions, because that's a DEM, in the more elevated regions, there is lesser number of rain gauges. And as a result, the rain gauges, this is globally, gets biased towards more flatter regions, regions closer to human settlements, whether it's a village or a road or whatever. So that's where it is. But this is how it looks like, and the statistics are in this paper. But if you look at the seasonal cycle, and again, you know, I'll leave you at the seasonal cycle, and that you can see the rain gauge sometimes doesn't capture those peaks. And that's sometimes obvious, because sometimes the big rainfalls occurs on the peaks of the mountains, and you don't have a gauge at the peak of the mountain, for example. So the rain gauge always has the lowest peak, and the TRIM and the CHIRPS, which are 2 independent sources. I do not think there's any mix between the TRIM and the CHIRPS estimates. these have much more than what's there in the rain gauge. So, second question, how important is precipitation in hydrological modeling? Okay? And obviously, if you don't have a proper input of precipitation, then you won't have a good output of hydrological model, because that's the rain, that's the water which is routed through your model to your outflow. Okay? So even for small catchments, precipitation is seldom spatially uniform, and interpolation of rain gauge data results in errors in streamflow simulation. So what we did was we took 6 catchments in this small country of Vietnam, which is pretty skinny, but it's pretty long. And one of them is the one which we do. I think we do the one with the one of the rivers over here. Okay? And so these are the S1, which is XL River Basin, S2, which is LS Basin, 6 of them. And so we focus on the first river basin, and I'll show you the simulation in a minute. But before that, we are looking at different products, because even with Earth observations and model products, there's a lot of different products. So we compare them to each other, and we want to make sure they all reasonably agree with each other. If one is completely different than the others, then we have to examine to see what's the reason for that. And we do this, and then, these are all written here. There's a lot of these over here. And then one thing we do is then we run all of these for the different catchments which I showed you in the 2 slides ago, and look at both A, Nash-Sutcliffe efficiency, and B, the percentage of the bias of the daily stream flow. And again, the Nash-Sutcliffe efficiency is the top one, and they have both calibration and validation, because we need to make sure the model, which is a soil water assessment tool, is calibrated and then validated. So when we do all that stuff, you can see that this particular product, which is iMerge version 6, and again, this paper is a few years old, so there is probably newer versions of this, has one of the best performances compared to the other products, which are also from the same thing. But the more striking result, for this particular catchment, if you look at that catchment, the S1, we do 2 experiments. The first experiment, we just use the rain gauge. I know this is a very small catchment. There's 3 rain gauges in this catchment. It's a very small catchment. And when you have just the rain gauges in the catchment and you're using a hydrological model, the model interpolates the rainfall from these rain gauges to feed it into, to create your overland flow and your stream flow. And you calibrate the parameters of the model in the first 10 years. You get the Nash-Sutcliffe efficiency of 0.8 and a percentage bias of minus 9.6%. And in the second part, you do the validation. You get a Nash-Sutcliffe efficiency of 0.74 and a percentage bias of 25%. Very simple, something which most students in hydrological modeling class will be able to run. But when you use this Earth observation of iMerge final version 6, the first part is again validation, because you have to make the new sets of parameters, because the parameters for the gauge will not work for the Earth observation. And you get 0.84 percentage bias, 2.9. It's a little better, but nothing to write home about. But where it does very well is the validation. Not only does it do very well and outperform the gauge, but it captures the peak flow. And the one thing which we really want is peak flow. I mean, that's the whole point of hydrology, to capture peak flows. Now, guaranteed, these are monthly, so this is not as great as having, daily, but that's where we move to. So, interpolating rain gauges results in errors, even for a small catchment. Because rainfall is so spatially heterogeneous that you will make lots of errors. And working with radars, working with UAVs, working with these distributed products for rainfall is the most important one. Oh. So this third question is, can we get higher spatial resolution of and deeper into the soil from Earth observation? Because, Earth observations, A, have low spatial resolution, and B, they're just looking at the surface. Can you go deeper, and can you get higher spatial resolution? Because most of the people who work in catchment hydrology, people interested in agriculture, biogeochemistry, they're more interested in the processes which occur at a more finer scale than 10 kilometers or 25 kilometers. I mean, whenever we hear about models that are 25 kilometers, somebody who's doing agriculture in a small catchment will say, what does that mean? Okay? So most Earth observations are spatially limited, especially in the case of soil moisture in microradiometry. The limiting factor is the antenna. And probably most of you learned how a microradiometer works in high school without knowing it. It's that double slit experiment which you do the diffraction, the Fresnel's law of diffraction. That's exactly what we do. So the bigger the antenna, the higher the spatial resolution. But the bigger the antenna, it's more difficult to balance it on the bus up there, 800 kilometers above the Earth, and it will take up more fuel because it's heavier. So then you run out of gas much faster. So there is a trade-off to keep a smaller antenna. So what happens is most of what we get are 10 kilometers, 9 kilometers, 36 kilometers. So what we did about 15 years ago, we came up with an idea of using the theory of thermal inertia to obtain higher spatial resolution of soil moisture. So if you think of soil moisture versus day-night temperature difference, I mean, you've all gone to the ocean. If you go to the beach at 2 a.m. and take the temperature of the water, and go to the beach at 2 p.m. and take the temperature of the water, it will be very, very small, like 2 degrees. And you can try this out. Or even the lake outside. But if you go to a desert and camp, let's say in Arizona, and you take the temperature at 2 a.m. and 2 p.m., it's about 40 degrees. So, ocean, very high soil moisture. Desert, very low soil moisture, high temperature difference. Now, of course, this problem on the land is that vegetation. It modulates this relationship. So vegetation makes this sensitivity flatter. So when it gets flatter, the sensitivity decreases. So we use this, we create a whole data set by standard models. I mean, this is called your lookup curve. And we make this lookup curve using 30 years of data, using monthly data of soil moisture versus surface temperature difference for varying vegetation indices. And then we use this to go to our big box of 9 kilometers and split it into smaller boxes of 1 kilometer. And the only adjustment we do is we average these 1 kilometer boxes in your 9 kilometer box, all 81 of them, and make sure the soil moisture then matches the average matches the average of the one from the 9 kilometer box. The only thing we do this, and this is all described in a paper in gory detail in this one over here, down here. So this is how it looks like. This is 1 kilometer, this is 9 kilometer. It's all global, it's all available online for you to download, and you can see that, the patterns look pretty similar. Unfortunately, at a global scale, it's very difficult to see the difference between 1 and 9 kilometers. And the same thing, this is the one for 400 meters, and you can see for 2022, April and July, you can see it looks pretty fine, but it's not too much, we can do the same downscaling as at the 1 kilometer as well as the 400 meters, because we have that surface temperature and vegetation index at that scale as well. Now this is where you start seeing some things. So you can see the 400 meters is all in this first row, and this is all 1 kilometer in the second column, and this is in the third column, and you can start seeing differences. And you can start saying, oh, where does this happen? And this was most recently published in Nature Scientific Data. But if we can go to smaller catchments like the Sacramento, San Jose, or the Danube River, and start seeing 1 kilometer at the top row, 9 kilometers in the middle row, 1 kilometer again here, and 9 kilometers here, you can start seeing a better pixelation of the 1 kilometer and start zeroing on those areas which are extremely dry or extremely wet. And this is important for land use planning, especially for agriculture or real estate or whatever. And this is the same thing you can see with the Danube River watershed. In this one, I put all the 1 kilometers in the first column and all the 9 kilometers in the second column. And you can clearly see over here the blurriness at the 9 kilometer as opposed to the more pixelation and the more details at the 1 kilometer. This is the same thing for United States. We start seeing some things, 400 meters, 1 kilometer, 9 kilometer. The 9 kilometers clearly shows much more blurriness or lack of resolution compared to the 400 meters. But nothing is as powerful as seeing a small watershed, the San Pedro watershed, only a couple of square kilometers in area. And if you look at the dry down, which occurs between June 18 and June 26 of 2018, it's nice and wet at 9 kilometers, then it gets drier and drier. But when you look at it at the 1 kilometer or the 400 meter scale, you can see this drying is so much more pronounced, with more drying in the south central area as opposed to some areas where the wetness remains. And these areas where the wetness remains, you don't see it at the 9 kilometer scale. So if you use the original data, you would miss that because it's not visible at that scale. And so we are using the dynamics of how land surface temperature varies with time during the day, as modulated by vegetation, to pick out high resolution soil moisture. And this thing you can do with any platform, with any model, with any lookup curves you want. It's the principle which is innovative. You can do it in many different ways, and you get the similar answer. So you can see over here, so these kinds of things are very important for catchment hydrologists to go in and look at setting, or people who are in other areas too, whether it is maybe even geotechnical engineering, you can go and say, hey, this is a place where it's always very bad. And again, this is only for the top 5 centimeters. This is surface soil moisture. So, you have to remember that. Now, if you say, oh, how do you know this is correct? Because, again, this is all global. So what we have done is we have chosen soil moisture networks. It's about 50 of them all over the world, many of them in the United States with USDA, US Department of Agriculture Soil Climate Analysis Network, USDA scan sites, and many. This one is in Texas, this one is Soilscapes in California, Remedios is in Spain. Lots of these, and we show these things, and then the big data sets are all analyzed together, and all of it is actually published in this article which I showed you, the 1 kilometer and the 400 meter articles. So this is all the different networks. This is the unbiased root mean square error. This is the spatial standard deviation. This is in those networks, how much does the soil moisture vary across the landscape, computed by in situ, computed by 400 meters, computed by 1 kilometer and 9 kilometer. Because, it's a spatial variability we are after. And so, we have done this, and most of the times the 400 meters shows the closest resemblance to the in situ data sets. So that's the in situ data sets. So that's the black. The black has, most of the times it has the most spatial variability because these are dense networks across these sites. And this data is available in, again, it's all public, it's all there, and these are public, and then you can go in and download it. It's at National Snow and Ice Data Center. The 400 meter data is available at UVA Dataverse, and again, a little bigger because of the size of the files. Now, the question arose that we are only doing the 0 to 5 centimeters soil moisture, which is very tiny. It's like, scratching the surface. Can we go deeper? And one of my students, most recently, I think, we just got it published in Remote Sensing of Environment. So this 5 centimeter, this is 20 centimeters, all global. So for the same period, 2015 to 2026, we have been able to go deeper into the soil, and this is all the statistics. Comparing it for the same sites, because all of these sites have soil moisture observations at deeper layers too, in situ. And so we compare our pixel, whatever we generate using these algorithms to. And now once you start going down to 50 centimeters, you're talking about real stuff, because this is the depth of the roots. Somebody told me that 1.5 meters is very important, because that is the depth at which they dig latrines in many of the developing countries of the world. So if it is very wet at 1.5 meters, then there is a greater chance for these microbes, these bacteria, viruses to migrate to the surface, etc. So there's a lot of applications of this, but you have to remember, as you keep going deeper into the soil, and this is what we are using a Richard's equation variant, as you go deeper into the soil, the RMSE starts increasing. So if you go these products, if you are looking at the surface, the 0 to 5 centimeters, you will have the best results. But you go deeper, you get lower results, and because all your errors get cumulative. But we do use the soil types for each pixel from FAO databases, because all of this is based on Richard's equation. And to give you a better one, this is the one which is just published. You can see over here. This is the International Soil Moisture Network. This is the estimated one, and these are the differences, with these things. So you can see that we are kind of mimicking what has, again, you can see this is at 50 centimeters. So that's the green, the red. So we have errors, but at the very least, we are getting the similar shapes of the profile, and this is over almost 5 years of data sets. So, and again, we are trying to do this and make this also available to the public so that they can use not just the surface soil moisture, but the deeper soil moisture. Now, one of the things I did when I came to UVA was I bought this gadget. It's one of the few things which cost more than my car. This is a fixed wing UAV with L-band radiometer. And this is, it's not very big, but the best part of this is that, let me see if I can make this work. So this can take off, it takes off air-powered. The only problem with this is the way it lands. And every time it lands on its belly. Unfortunately, it jars something every time. So now pretty much it's become a paperweight. It's broken enough time. So my next set of instruments I'm going to buy are quadcopters, which you have all seen, so they can land up and down. They are a little slower. See, this goes very fast. So you can map a lot of area, but unfortunately you can't land. So the quadcopter, you can buy 3 quadcopters for the cost of one of these. So hopefully we can do a better job mapping it. But this is the future, because this is where the future lies, and this is when it was working, everything was working. We published this 5-meter soil moisture maps, 5 meters. And again, surface, but 5 meters. So you can imagine that you can get very high resolution soil moisture. I call this remote sensing on demand. So you can just go out, fly it, get it, and you're done. You don't have to wait for, the NASA satellite. They have latency. It doesn't come out every day. So if a NASA bird flies over, you have to wait for a few days, 48 hours or so. But this, you can get it right away and do it. So now the last challenge is, how do we study un-gaged and poorly-gaged watersheds? Because most countries of the world either have streamflow data which is not really, trustworthy, or they don't share it with you. For example, India doesn't share any of its major river data because they are very worried it is national security. So how do we do that? So one of the things which we did, we used AI ML to train the data, to train in data in rich regions to streamflow in data poor regions to do that. And this is what we call as transfer learning. This was a project which I conceived of taking hikes with a friend of mine who was in systems engineering, with Peter Bailey. And so we went and pitched it to the Army Research Office and loved it. And 4 years later, 5 years later, we have 4 publications and hopefully getting more money on this topic. So something which I never did before, and again, it was a chance encounter, just going on a hike with somebody, and I'm not a hiker, so it was very exciting to do this. But so what is the understanding? If everybody who knows global hydrology knows this, that we in the West are spoiled. We have lots of data. I mean, I always tell my Indian counterparts, if you want to know the level of the river in Charlottesville, all you have to do is water.usgs.gov. Then you can see the level of the water right now. It doesn't take an act of Congress to get the data. But in India, you can get it, even with an act of Congress, because it's all embargoed. You can get it. So here in the West, and in South America, and in Europe, there is one stream gauge for about 11,000 square kilometers of watershed. Lovely. But if you go to the data sparse regions, and again, remember, look, the Ganga Brahmaputra is empty over here. There's no data over here. There is about one stream gauge for 90,000. So it's 9 times as much worse. It's just because there's not enough stream gauges, B, not enough sharing. Both have it. Or C, not trustworthy. That part I don't even go to. So what we did was we tried to do 14 static variables and 2 dynamic variables, precipitation and air temperature. And the static variables are, variables you all know, like average slope, population density, soil properties like bulk density, clay content, height over sea level, all these kinds of things, irrigation area. So we are feeding this into your ML. And then these are the 8 prediction skills, 8 metrics of prediction: Nash-Sutcliffe efficiency, log of it, correlation coefficient, Klein-Gupta efficiency, mean deviation, relative difference, all these things. Okay, these are all standard stuff, and it's all in that paper. I think if I've not shown it to you, I will be happy to share this paper. So then we defined a concept of hydrologic similarity. S is the source, T is the target. S is the places in North America, South America, and Europe. And T is the target in Africa and Asia. So if you can do an L2 north and do this, if this is small, that means your source and target are similar hydrologically. And this is all of them, all 16 of them. The 14 static variables and the dynamic variables. Because, if you are taking results from a catchment in Wisconsin and applying it to a catchment in Senegal, it's not going to be very good. Because you have more vegetation here, you have a different climate here, you have different rainfall here than Senegal. So you want to get the right answers for the right reasons, rather than using AI ML as a black box. So that was our concept. So what we did was we took the output of this NASA publicly available model called GLDAS, Global Land Data Assimilation System, and compared it to the runoff. This is yearly runoff. It's monthly runoff. Sorry, I take it back. A monthly runoff for a place in Afghanistan. There's a catchment in Afghanistan. And you can see, we're not doing any tuning or anything. This is available. We just put it, and you can see all these high runoff values which are missing. Then we trained one on S2, S3, which is South America and Europe, LSTM, and applied it to Afghanistan. You can see you do a bit better. And then we do one with just training in North America and applying it on Afghanistan. You don't do as well. And we have many, many combinations of it. And these radar plots are very good. If you get once on everything, then you are perfect. The smaller the area inside the radar, the worse you did. So you can see this one obviously did very well, as is apparent that it is capturing these things. And still better is the fact that if you take the number of experiments where your LSTM, your transfer learning, is doing better than the physical model, GL DAS, and all, at least 5 of that indices, 5 of these, 1, 2, 3, 4, 5, 6, 7, 8, 5 of these are positive, okay? Then if you just use the dynamic variables for your difference, the difference between the source and the target, and this one uses static and dynamic variables, the number of experiments, the more number of experiments will coincide with better success when your distance, hydrological distance, is shorter. So this makes sense. So we are saying that if 2 catchments, the source catchment and the target catchment, and the source we use more than 1 to lump it in, if they are closer to each other hydrologically, both with static and dynamic variables, the closer they are in the D2, that is lower D2, the more chances you have is the experiments, more experiments will result in success. Which is trying to get the right answers for the right reasons rather than throwing everything and creating a value. And you know, I mean, people have got good R squares even without doing hydrological similarity, but we want to go through hydrology. So, trying to wind it up, integrated assessments of floods and droughts. This was a publication done many years ago in which we just used precipitation from satellite sensors, runoff from a model, evapotranspiration from a sensor with a model embedded in it, and the gravity emission for water equivalent thickness. And you can see a dry as seen in this Newcomb River Basin, and this has China as well. In January 2005, results in dry runoff or less runoff in March 2005, low ET in March 2005, and then in May it reflects lower values of the total water because the signal goes from the atmosphere to the surface to the subsurface. You know, groundwater also depletes. And the same thing you can see in September 2011, wet, more runoff, more ET, and more water storage. Okay. And that one was Mekong, and this is Murray-Darling, and you can see the same thing, except in Murray-Darling, the swing from dry, August 2009, to wet, January 2010, it's a matter of months. And actually, January 2010, there was huge flooding in Sydney and in the Murray-Darling River. I don't know if you guys remember it, huge amounts of flood. So you can see that, you know, this signal propagation is very, very interesting because all of these 4 variables are from 4 different methods and none of them talk to each other. It's not like I used one to calibrate the other. They're all independent. You can see that using a combination of earth sensors and models, we can tell a coherent story. So, you know Amazon, everybody over here, many of you may have gone there, and then Murray-Darling in Australia. So for people who are interested in hiking and boating and all that good stuff, that's the place to go. Except watch for the crocodiles or boa constrictors or whatever else there may be, pythons maybe. But Murray-Darling is a managed watershed. You know, they have a lot of agriculture, they grow a lot of animals, a lot of stuff, and lately they've also been growing lots of wines and all that, you know, grapes to make wines and all that stuff. So if you define a very simple index called monthly rainfall anomaly index, where you take the monthly rainfall anomaly and divide by the monthly climatology, this is how Amazon will work. So the Januaries are all very close to each other, Februaries are all very close to each other, Marches are all very close. So they don't vary much. one January to the next January, not much variation. And remember, this is dimensionless. Anomaly index is dimensionless because you're dividing rainfall by rainfall. Okay. Now the same thing for Murray-Darby looks huge. Huge fluctuation. It's the same units, no units. I always joke when I put this slide up, I say, you know, I still can run 100 meters. Maybe in 25 seconds, maybe, I don't know, 20 seconds. But after that, my heartbeat may look like this. And that of Usain Bolt in his prime is like this. So the precipitation is the heartbeat of an ecosystem. If it has a steady beat, it's healthy. Unsteady beat is unhealthy, causing more extremes. Something we don't control. It's controlled by climate and weather. So many applications of our rainfall and soil moisture have gone on to other places. If you don't recognize, this is Chile. And what we have found, and this was published like a few weeks ago, decrease in soil moisture in the days leading to the fire. So this is earlier, this is later. And this is how it looks. So for the control areas where it didn't burn, your soil moisture peaks at 0.2 is volumetric. For the areas which did burn, there's a lot more pixels with 0.1. And drier areas burn faster. Again, you need ignition. You know, you can't just, make a fire. You need ignition. Hopefully, if nobody ignites anything, and if nature doesn't cause us a lightning or a big windstorm which may cause trees to, catch fire, you'll be fine. But most of the times, the dry areas, and this we did with soil moisture from earth sensors from SMAP, you can see that those are the areas which do. So, trying to set the future, so hydrological model has evolved over the past 3-4 decades, and now we know very well how to put in earth sensors, how to put in satellite data information, etc. People are too impatient of AI now. They wanted to solve everything yesterday. And one of the biggest dangers I see from this is that somebody sitting in Washington or Paris or Geneva or in Sydney thinks, oh, AI ML can solve it, we don't need rain gauges anymore. AI ML works only when you train your model. If you don't have stuff to train it, forget it. And this is the false impression caused by people who say you don't need hydrology, you can solve everything by AI ML. I mean, you can't sit on the branch of a tree and say I need firewood and chop it. That's what they do. And the thing is that we need more observations. Actually, if you want to study hydrology of Africa, you can't do it with AI models now unless you try to use some hydrological similarity argument which I showed you. Because you don't have enough. And so the more the observations, and we're discussing with many of the students in this department, you have access to less expensive instruments. You can put in a sensor in a lake 10 miles away, and it's only $20. So, it will give you data for 6 months, then you can put another $20 instrument. That's the way we collect data. You have to collect more data, not less data. And I think I get the feeling people are thinking that AI can do everything, we don't need to do anything. So, I hope that long-term in situ observations is continuing. And this was me and my group last year at the AG meeting. Again, there's some people, one of my former students, he came with 6 of his own students, or 7 of his own students. So that's why the big group here. So we went and did a big meeting. I was reading the New York Times, and this is where I started my career after grad school at the Goddard Space Flight Center. I guess, Dan, you were there too. And so Robert Goddard was the inventor of the human rocket, inventor of the American rocket. And guess when he flew it first? 100 years ago yesterday, in Worcester, Mass. This is a big story in New York Times, that's how I read it. So he said, it's difficult to imagine what's impossible because the dreams of yesterday are the hopes of today and the reality of tomorrow. So, thank you very much.
Thank you, Venkat. Really appreciate the talk. We'll take a little time for questions if we have some from the audience or online.
Yes.
Yeah, thanks for your presentation. So your AI model for the engaged basins and engaged required pricing. I have two questions about that.
Sure.
The first one is that did you do any fine-tuning of the model when applying to your other bases?
No. You have to use the same thing. So we only use the standard data which is available. All the data sets which we used are the ones which are publicly available global data sets. So that's a condition. You can't expect the government of Afghanistan to give you any data. You just use what is available globally.
Yeah, so my question is like, it might be like improve the performance of the model for bases with like large like hydrological or low hydrological similarity. For bases with low hydrological similarity, you think it's possible to improve the model with like not just the transfer learning and but also fine-tuning. Yeah, thank you.
So you say that there are two basins. So, but my point is, if you calibrate your LSTM or train your LSTM in Wisconsin, you can only apply it to a catchment which has hydro-eco-climatology similar to Wisconsin, and that's those 16 numbers. You can apply to anything you want. If you use 1 trillion observations, you can make anything fit because AI/ML is nothing but curve fitting. I mean, think about it. Neural networks, AI/ML, it's like an n-dimensional curve fitting. You can fit any curve to anything you want, but you want to fit it for the right reasons, and then figure out. One of the things which I've been very intrigued, and one of the students asked me this yesterday. I think. So, what's the new thing in AI? I think you asked, Aaron asked me. I think it's explainable AI. So can you explain something? And I guess that's where we can earn our paycheck by doing it.
Yeah, just my polling question, like you use like 14 variables in the model. So have you checked which variable contribute most?
No, we have not done that. That's one of the next steps. But the point is that those are static variables. I think the biggest contribution is the dynamic variables, the P and the air temperature, the precipitation air temperature. In those 14, which one is the highest? I think we have a publication, but not for this particular watershed, but we have for other things, the explainable AI. For example, we have been doing this in Colorado River Basin, in the upper Colorado. The biggest contributor, snow melt. But unfortunately this year there's no snow to melt, so that's a different story.
Other questions?
Yes.
I have one for you, Venkat. I work on high elevation mine sites in the Pacific Northwest. And they're typically elevation 20,000 feet. And all the hydrology at those sites happens within a matter of 3 or 4 weeks. Precipitation that's falling in late November through March accumulates as snow melt. And then one day it starts getting warm, and in a matter of 10 days, all of it melts, goes straight in. And it dominates the hydrologic system. But it's really difficult to predict. I try to take one of my models and predict the hydrology that I'm lucky if I'm kind of lucky. So I wondered how that built, how you could build some of that temporal component of not only precipitation and essentially land use, perhaps maybe the way of saying it, but in the context of I'm actually storing water on the land surface of snow.
So that's all temperature. One good thing about air temperature, which is not good about soil moisture, is air temperature is constant over a little larger area. So you don't have the air temperature here and in the next building won't be different. But the surface temperature, land surface temperature, and the soil moisture is going to be completely different because it depends on land type. So if depending on the area of your study, how big it is, mapping snow can be possible because all what you have to do is fly a LiDAR in the dry season, let's say in April or May, when there is actually no snow, and then fly a LiDAR in January when the snow is at the maximum, and you can figure out the thickness. Then the second question is and you can even fly a UAV. I mean, UAV LiDARs, I'm sure they can fly at that if you get the permissions to fly over there, especially if it's not a big area. The second question is that how do you do the melting thing? So in hydrology, we have a whole bunch of those. Of course, if we can get some stream values, runoff values at some point, a weir or something, then we can set a model, a simple model, based on previous year's observations and try to use it. I mean, snow melt is one of the most important things. Right now, in Southern California, it's 80 degrees. So the biggest worry in California is the snow in the Sierras is going to melt prematurely. You don't want it to melt at least till mid-April or late April, because that's when you need the water. If you melt it now and go away, then you lost the water. So it's possible. And the second answer to your question is that if the physical models doesn't do well, you can throw some of these things, because sometimes we can't account for all the processes. If we have enough observations, we can throw it into AI ML method and see how it does. But we need observations. The problem with all of this is observations. But if the area is small, then getting an idea of the snowpack is reasonably easy. If the area is very large, then you have to depend on other ways of doing it.
Like snowpack measurements and solar equivalents.
That's more than enough. Yeah.
Snow melt models.
Yeah.
If you close your eyes, they're good.
Snow melt is tough. It's a very tough one. Yeah. And also, not all snow is similar, because every snow has a different density. The snow water equivalent and the fluffiness of the snow determines the melt rate. And yeah, it's very complicated, and actually it's a problem, which requires a lot of attention.
I think your time will wrap up there, but I'm sure Venkat can sit around for a few minutes if you have another question or two. But let's get him another